Hello, everybody. My name is Pedro Valero-Lara. I'm a computer scientist at ORNL, Oak Ridge National Laboratory. So in this talk, I'm going to present some ideas for the implementation of heterogeneous code by using OpenMP tasking and target GPU offloading. First, let me introduce myself. As I said, my name is Pedro Valero-Lara. I'm a computer scientist working at Programming System Group at Oak Ridge National Laboratory. So this work is part of the ECP project Proteus Toon, which is led by Jeffrey Better. The motivation of this talk is presenting and evaluating some ideas about heterogeneous programming by using OpenMP task and integrating OpenMP task or integrate the GPU loading in OpenMP tasking. As an example, we have used a heterogeneous implementation of the BLAS-free TRSM routine. At the end of this slide, I also propose some ideas to make the implementation of heterogeneous code using OpenMP much simpler by using OpenMP target task or OpenMP target tasking. So the sample code that we have used to evaluate these ideas is TRSM, triangular solve. This is one of the most popular BLAS Level 3 routine and is used in many applications. This routine basically computes the equation A as equal B, where A is a triangular matrix. It can be lower or upper triangular. So the parallelization of this routine, of this code, is consists of discomposing the matrices A and B into tiles. Doing that, we make the computation in parallel, so we can make some of the computations that we have to do on different and separate tiles in parallel. The main operation that we have to do, or the main task that we have to do, correspond to two different BLAS Level 3 routine. One is TRSM. That we have to, for TRSM, we use as input the tiles of the A matrix in the diagonal tiles of the A matrices. And then once we compute TRSM, we can compute a set of gems. So there are data dependencies between these two main operations. So the parallelization and also the data dependencies between the tiles and the operations can be described or can be implemented by using OpenMP task. So for our heterogeneous code, we decided to decompose the operations by using CPU to compute the TRSM and compute the gem on GPU. So although gem is an operation that can get a very good performance on both CPU and GPU, TRSM is not so GPU friendly. I'm not saying that TRSM is not able to get a good performance on GPU, but the performance that you can get computed TRSM on GPU is not as high as the performance that you can get computed gem on GPU. So we decided to compute the TRSM operations, the TRSM task on CPU while using GPU for the gem task. Something to mention, something that I think is important to mention is that although in this talk we focus on this operation, this BLAS-free level operation of routine, this operation is also very similar to the rest of BLAS level 3 routine, and also some or many LA pack routines. So the code that we have, we are going to present in the following slides, can be the way that we implement that code and the things that we are using in the code can be also applied can be applied to other BLAS level 3 routine or LA-pack routines, but probably can be also be applied to other applications. So first, here I'm going to present the first heterogeneous code that we implemented. For this code, we use a unit for decomposition. So it means that we use the same tile size to decompose both matrices, A and B. If the tile size is not very big, we can have a high number of tiles and then a high number of tasks. So we have to be careful with the tile size that we can use. I mean, in the smaller tile size, the higher number of tasks we have to compute, and we have and then much more parallel code we will have. The problem of that is that if we make the tiles too small, we are going to get a very low performance on the operations that we have to do on these tiles. So the idea is to have a good enough, or to have a big enough tile size to have enough task in the computation to make the computation parallel, but at the same time get a good performance in every other task that we have to compute. So on the right, we can see an example of the code that we implemented, a pseudo code of the code that we implemented. As I said before, we compute TRSM on CPU while GEM, matrix multiplication, on GPU. So in this code, we see 4 different kind or type of pragmas. The first one is the OpenMP tasking. So basically, we encapsulate in one task one operation, one TRSM or GEM operation, and also we describe or include the dependency, the data dependencies to compute that we must respect to compute that task. That is what we do on CPU. I mean, on CPU, we don't need anything else to make anything else or any more pragma OpenMP to make the computation. But on GPU, we need at least 3 more pragmas. One of them is OpenMP target enter data map. This pragma, what this pragma does compute is the data movement or the memory transfer from CPU to GPU. Similar to this, the last pragma that we use is the OpenMP target exit data map. This is basically the same operation that we do before in enter data map, but moving the data in a different direction or in the opposite direction. I mean, from a GPU to CPU. In between, what we have is OpenMP target data use device pointer. This is just to specify that the pointers, the tile underscore A, the tile underscore B, and the tile underscore C are GPU pointers. I mean, they are pointers where we have moved the data that we are going to compute on GPU. So as you can see, we need this. We need an extra pragmas to make the computation of one OpenMP task on GPU. So basically, as we can see here, for the GEM operations, we integrate OpenMP target, in particular 3 different OpenMP target pragmas, into one OpenMP task. Additionally, we have implemented one more code. But in this case, instead of using a uniform decomposition of the matrix, we have used a non-uniform decomposition, in particular for the B matrix. I mean, we use the same decomposition for A matrix, but a different decomposition for the B matrix. The motivation of doing that is maximize the use of a GPU. Unlike CPU, where we can saturate one CPU or one core by using or by computing a relatively small data or a small matrix or tile, on GPU, we need much more than that, or a bigger data to saturate the GPU. No, but using a different decomposition of the B matrix, we are not only able to maximize the GPU computation, but also reducing the number of tasks, sorry, the number of CPU GPU transfers, which is very important for the overall performance. And also making the tile of B matrix bigger, we are able to get a higher IPC or higher performance on this operation. In general, for GEM, the bigger the data, the higher performance. In terms of modification in the code, or in terms of programmability, this different matrix decomposition doesn't require many modification in the code. As we can see in the code, we have removed one for loop, in particular the one that was used to going through or to go through the different columns of the B matrix, or the different column of the tiles of the B matrix. In this case, as we have decomposed the matrix into a block of rows, we don't need that for loop. So in general, this code requires much less, not much less, but a few less number of codes than the previous one. In order to make the analysis more complete or more general, we have also included in the analysis, optimized CUDA code for the same operation. So basically, we implemented a heterogeneous code using CUDA, on top of CUDA, using the non-uniform decomposition of the matrix, but basically the same code or the same algorithm, but using CUDA. As we can see on the pseudocode on the right, the implementation of this code using CUDA is much more complex than using OpenMP. And it's also much less transparent. We have to deal with the synchronization, with the CPU, GPU synchronization using stream, asynchronous APIs explicitly by using vendor functions or CUDA functions, and also CUDA data type. Apart from that, also the communication, the CPU, GPU communication must be implemented explicitly, again, using asynchronous API, CUDA, specific CUDA data type, etc. So, and not only that, also the combination of the use of different libraries, not only CUDA and cuBLAS, but also the CPU library, make the implementation more complex. In terms of number of lines, I don't remember exactly the number, but this CUDA code, or the implementation of the CUDA code requires much more number of lines than the implementation of the OpenMP code. So in terms of performance, we have used one node of the SAMI supercomputer. The SAMI supercomputer is composed by 2 IBM CPU Power 9 processors and 6 NVIDIA GPUs, Volta GPUs. But in this case, on this analysis, we have used the two IBM processors and one NVIDIA GPU. On the right, we can see the performance analysis comparing the performance of 4 different codes. The gray line corresponds to the optimized CUDA code, but doing the implementation synchronously. I mean, the memory transfers and the CPU and GPU computation, everything is done synchronously. I mean, we are not using CPU and GPU at the same time, as well as any computation on CPU, either on CPU and GPU, and at the same time, then transferring data either from CPU to GPU or vice versa. So the green line corresponds to the same code than the gray line, but doing the computation asynchronously. I mean, every computation is done asynchronously. I mean, we are able to compute, to make computation on CPU and GPU at the same time, and also doing some any kind of computation either on CPU and GPU while transferring data from CPU to GPU or vice versa. So it's a fully asynchronous code. For OpenMP code, we use the 2 different OpenMP code that we have seen previously. The one that makes use of a uniform decomposition of the matrix, and the one that where we have used a non-uniform decomposition of the matrix. For the CUDA codes, as I said before, we use in both of them, we use a non-uniform decomposition of the matrix. We can see in the performance, well, the performance is measured in terms of gigaflops. So, and we have used different matrix sizes. So in general, what we can see here is that the use of non-uniform decomposition of the matrix is much more efficient than decomposing the matrix uniformly. It makes sense because, on a heterogeneous system where we have, in this case, we have 2 CPUs and GPUs and 1 GPU, this architecture have different characteristics and can be saturated in different ways. Or, no, in fact, they are saturated in different ways. So a non-uniform decomposition of both operations. I mean, remember that we have 2 different operations which are different each other. They have a different complexity, a different memory access pattern, and not only that, but also non-uniform decomposition of data can is proven to be very efficient for heterogeneous systems. Okay, where again we have also different architecture with different characteristics, with different peak performance, with different bandwidths, etc. So the OpenMP code using a non-uniform decomposition is able to get much better performance than the uniform one, or the OpenMP code using a uniform decomposition, in particular on small or medium-sized matrices. For CUDA code, we see that in most of the cases, the performance get by the CUDA asynchronous code is much better, not much better, but better than the OpenMP or the heterogeneous OpenMP. But even if the OpenMP code is get lower performance, the OpenMP code is able to get something about 85 and 95 performance of the code. It means that even if we are not able to beat optimized CUDA code using OpenMP task and GPU offloading, we are very close to get the peak performance or the performance that is get by an optimized CUDA code. But the code, the OpenMP code, is much more simpler, much simpler than the CUDA code. So in general, the programming productivity of using OpenMP task or integrating GPU offloading inside OpenMP task for heterogeneous code, it's much higher or much better than CUDA code. Although the current specification of OpenMP is relatively easy to use, I mean, the integration of Target with OpenMP tasking is relatively easy to do. I think that we have a space for to make something even more simpler or much simpler than that. I mean, in the current specification, we need at least 4 different pragmas we see at the bottom of the slide to make to integrate tasking with target load. Unless we need one OpenMP task pragmas, and we need 3 target target pragmas. I think that we could integrate, we could use, well, we could integrate these 4 pragmas in just one single pragma, just adding one clause, one word in the OpenMP tasking. As we can see in the middle of the slide, just adding target before task, we can assume that the computation encapsulated into that task and also the data that is describing the dependencies is going to be used and computed on GPU. So this could make the specification much simpler for heterogeneous code, or even for GPU code, or OpenMP GPU or OpenMP heterogeneous code. But not only that, that also allows us to minimize the memory transfers between CPU and GPU. In the previous scenario, even on in the previous code, on the code that we implemented, even using a non-uniform decomposition, we have to deal, or we have to make some memory transfers between CPU and GPU that are not really necessary, because some of the computations of some of the data that we have on GPU can be reused for other tasks that had to be computed later. But that is very difficult to implement in the current OpenMP specification. By using a new OpenMP task pragmas, what we call OpenMP target task, we don't have to deal with that, and it could reduce the memory transfer between CPU and GPU in this heterogeneous code. I think that this is, oh, sorry, this is the latest slide, the last slide. So as conclusion, non-uniform or non-uniform workflows or graphs using tasking have important consequences or important impact on performance, in particular for heterogeneous, on heterogeneous system. Well, heterogeneous OpenMP is possible. I mean, we can use OpenMP not only for GPU only execution or CPU only execution, but for heterogeneous code. I mean, for heterogeneous execution using CPU and GPU at the same time and simultaneously. We made that. We use both CPU and GPU by iterating target offloading with OpenMP tasking. And even although our code is not able to beat an optimized CUDA code, we get a very similar performance with much less programming effort. So basically, the idea for using OpenMP task and target offloading or integrating target offloading inside OpenMP task looks like a good idea to get a good performance on for a heterogeneous system. We propose OpenMP target task to increase the programming productivity, to make the code, OpenMP code, even simpler for a heterogeneous system, or to implement heterogeneous code, and making the specification even more transparent and more efficient, in particular, more efficient for CPU and GPU communication. So I think that this is all. So thank you very much for watching the video. And I hope that you enjoy the talk. If you have any question, please just reach me or send me an email. You have my email address in the first slide, well, in the second slide of this talk. Again, thank you very much for watching and have a wonderful day. Thank you so much.